So this is just a plot of this for a that is greater than 0 and less than 0. Okay. Now you can see a similar trade-off as in the previous example, right? Because if you pick a to be small, okay? If you pick a to be small, then, okay, if you pick a to be small, then the attenuation here, okay, will attenuate slower, right, as omega increases. But for a that is small, it decreases, the response decays rapidly in the time domain, okay? Now, vice versa, if you pick a to be large, right, let's say close to 1, then this response will decay very slowly, right? The time signal decays slowly, but the frequency domain, right, attenuates rapidly, okay? So for a that is large, you will be able to obtain a low-pass filter with a narrower passband, right? You can be more specific about which frequency components you let through, but then you have to sacrifice the response time of your system, okay? So again, this depends on which trade-off is more worth it in your application. So this finishes up chapter 3. And again, in chapter 3, we're mainly looking at the Fourier series representation of periodic signals, both in the continuous time case and in the discrete time case, okay? So we now know that for periodic signals, we can always write it, right, at least most of the time, we can write it as a linear combination of these pure frequency components at integer multiples of omega naught, okay? All right. Now, what about a natural question is, what about, aperiodic signals? What about, regular signals that we would see that may not necessarily be periodic, okay? So this is the subject of chapters 4 and 5. So in chapter 4, we want to extend this concept of representing a signal as linear combinations of these pure complex exponentials, okay, to the case where the signal may not be periodic, okay? And we start with continuous time in chapter 4, and then we repeat the whole discussion again for discrete time signals in chapter 5, okay? So if you understand chapter 4, right, we will probably go faster through chapter 5, okay? All right, so the main idea is like this, okay? The main idea is like this. So we now know how to write out the Fourier series representation for periodic signals, okay? Now, for the insight here is that, for aperiodic signals, we can actually view them as periodic signals with period that go to infinity, right? So if we have a periodic signals where the replicas are distanced at a time that is repeated at a time capital T that goes to infinity, then we're essentially looking at a aperiodic signal, right? Okay, so that's the insight here, okay? So we start out by looking at this periodic square wave that we already discussed several times already, okay? So here we assume we have a periodic square wave signal x of t that, it has a period capital T, right, but is equal to 1 only from minus t1 to t1 and 0 everywhere else, okay? So since this square wave has period capital T, omega naught is 2 pi over capital T, and the corresponding Fourier series coefficient ak is this 2 sine k omega naught t1 over k omega naught capital T, okay? And if you recall right, this can be viewed as samples of what we call a sinc function, right? A function that peaks at the origin and then ripples away as the frequency increases. Okay? So this Fourier series coefficient can be viewed as samples of an envelope function that takes on the shape of a sinc function, okay? Or in particular, right, if you multiply t to the other side here, this tak are samples of this 2 sine omega t1 over omega at integer multiples of k omega naught, okay? At integer multiples of k omega naught, okay? And omega naught here is 2 pi over capital T, so you can also view this as k times 2 pi over capital T. Now here, x of t is a square wave going from minus t1 to t1, and it is repeated every capital T, right? It's repeated every capital T. Now, as long as you fix t1, right? As long as you fix t1, this envelope function does not change, okay? But as you increase capital T, right, even though this envelope function doesn't change, but as you increase capital T, which is the period of the signal, right, as you stretch the periods further and further apart, then you're essentially sampling at denser and denser points of this function, okay? So as capital T increases, this 2 pi over capital T becomes smaller and smaller. So this means that you're sampling at denser and denser points of this sinc function, okay? And this also means that, right, because AK corresponds to a frequency component that is at a integer at k times 2 pi over t, this means that you're also, this signal now has frequency components that are closer and closer to each other. Okay, you have more and more frequency components. Okay. So to visualize this, suppose you consider a square wave like this. Okay. So here, this square goes from minus t1 to t1, and it is repeated every capital T, integer multiple of capital T. So for this specific example here, we're taking t equal to 4 times t1. Okay. So here we have t equal to 4 times t1. Okay. And in this case, right, this t over ak, right, which is this thing here, will be sampled, okay, will be sampled at, integer multiples of 2 pi over 4t1, or let's say pi over 2t1. So you would be taking samples at 0, okay, at, omega naught, 2 omega naught, 3 omega naught, so on and so forth, okay? Now, suppose you increase the period by 2 times, right? So you stretch them further away to the case where t is equal to 8t1, okay? So when you increase the period by 2 times, you're essentially sampling at twice the frequency of this signal, okay? So when you increase the period by 2 times, instead of just sampling at this point, and this point, now we have an additional sample in between every 2 points, okay? So we're sampling at twice the frequency, okay? Now, if we further stretch this, okay, more to t equal to 16t1, okay, then you would be sampling the sinc function even more and more denser than before. Okay? Right. So this also means that for a larger period, right, for a larger period, you're considering frequency components that are, denser and denser, right? You're considering more and more frequency components. The separation between consecutive frequency components becomes smaller and smaller and smaller, okay? So if you continue in this fashion, right, suppose you set this t going to infinity, then you would expect that the sampling of the sinc function would converge to the continuum of this function, okay? So in the limit, as capital T goes to infinity, we eventually see just one aperiodic pattern, okay? And you expect that the frequency components will also converge to a continuum. Instead of having discrete frequency components, right? Instead of having discrete frequency components at k omega naught, we now may have, a continuum of frequency components at all frequencies. Okay? Right. So the key insight here is that, we can view aperiodic signals as the limit of a periodic signal at t going to infinity. Okay. So this is the insight, okay? But we can look at this a little bit more carefully. Yeah. Okay. Now, suppose that we're interested in looking at the Fourier analysis of this aperiodic signal x of t, okay? So suppose we have a signal x of t that is of finite duration, meaning that it is non-zero only within a certain finite period. Okay, so suppose that x of t looks something like this. Okay? And with x of t, I can construct a periodic signal x tilde of t by repeating x of t every integer multiple of capital T. Okay? So x of t is the signal that we're interested in. But given x of t, we can construct a periodic signal x tilde of t by repeating it every integer multiple of capital T. Okay. Now, x tilde of t is periodic. So we know how to write the Fourier series representation of a periodic signal. Okay? So for x tilde of t, which is periodic, we know that we can write it as a linear combination of e to the j k omega naught t, right, where omega naught is 2 pi over the period capital T. Okay? So here omega naught is 2 pi over capital T. Okay. And how do we find the coefficients? We find it by taking 1 over t, the integral of the periodic signal x tilde of t, times e to the minus j k omega naught t, integrated over one period. Okay, doesn't really matter which period we're looking at, but just integrated over one period. Okay. Now, when we integrate over, one period from minus t over 2 to t over 2, right, we're essentially, right, integrating over one of this x of t, okay? So when we're integrating over this range, we're essentially integrating over x of t from minus infinity up to infinity. Okay? So ak you can view as 1 over t, the integral of this aperiodic signal times e to the minus j k omega naught t dt. Okay? Now, this integral is very important to us. Okay? So let us define this integral as capital X of j omega, okay, which is the integral of x of t times e to the minus j omega t dt. Okay? So you can also view this as sort of taking the inner product between the signal x of t and the complex exponential e to the j omega t, right? So when you take the inner product, you would have a complex conjugate in the second part. So inner product sort of gives you the projection of x of t onto the direction of this complex exponential. Okay. So this capital X, if you define this integral as capital X of j omega, then what you have here is this capital X evaluated at k omega naught. Okay? So for the periodic signal x tilde, ak is 1 over t capital X evaluated at k omega naught. Okay? So that's what we wrote here. Okay? Okay. So then let's take this and plug it back into the Fourier series representation. Okay? So I want to take that and plug it back inside here. So therefore, x tilde of t, you can write as the summation of ak, right, which is 1 over t capital X of j k omega naught times e to the j k omega naught t. Okay? Now, by the fact that omega naught is equal to 2 pi over t, or equivalently, t is 2 pi over omega naught. Therefore, if you take this and plug it inside here, what you get is 1 over 2 pi times omega naught. Okay? So I'm substituting this inside t, and this will give me 1 over 2 pi times omega naught, and everything else is the same. Okay. Now, what is this summation here? Okay, what is this summation here? Now, suppose we consider the function x of j omega times e to the j omega t. Okay. So when you look at this part here, this part is actually the value of this function at the point k omega naught. Okay? So suppose that this is this function here, and this value is the value at this point k omega naught. Okay? So this value times omega naught, right, times omega naught, assuming it's the width here, gives you the area of this bar region. Okay? Right? Any questions here? Okay. So this is for k, right? So if you go on and look at k plus 1, then this will give you the value of k plus 1 omega naught, right? The value of the function at k plus 1 omega naught times omega naught, which will give you the region of the square over there. Okay, so for k plus 1, you get this area here. And then for k minus 1, so for k minus 1, you have this region here. For k minus 2, k minus 3, so on and so forth. Right. So what you have here is basically 1 over 2 pi times the sum of all these bar regions. Okay? Now, as capital T goes to infinity, or equivalently as omega naught goes to 0, right? What you have is basically the Riemann integral, right? As this becomes smaller and smaller, eventually this summation will converge to the Riemann integral of this function here. Okay? So as t goes to infinity, or equivalently as omega naught goes to 0, this summation converges to the Riemann integral of this function x times e to the j omega t. Okay? Scaled by 1 over 2 pi. Okay. So what this tells us is that indeed in the limit, okay, in the limit as capital T goes to infinity, right, meaning that, okay, as this capital T goes to infinity, right, x tilde is essentially x of t, okay? So as capital T goes to infinity, we can express x of t as this continuum linear combination of these complex exponentials, okay? So this is a linear combination of these complex exponentials over a continuum of frequencies, okay? So for periodic signals, the signal x of t is just a linear combination of discrete frequency components. But when x of t is aperiodic, it can be a linear combination of uncountably infinite frequency components. Okay? And this x of j omega then specifies how much of this frequency component is contained in the signal x of t. So therefore, we refer to this x of j omega as the spectrum of the signal. Okay? So interestingly, right, here we're defining x of j omega as the integral of x of t times e to the minus j omega t dt. So like I mentioned previously, if you think of this as the inner product between x of t and e to the j omega t, then what this is doing is extracting out the projection, extracting out how much of x of t lies in e to the j omega t. Okay? So given x of t, you can find how much, right, how much of the frequency component omega is contained in the signal x of t. And also, if you are given the spectrum capital X of j omega, you can actually reconstruct the signal x of t by taking a linear combination of these frequency components scaled by this spectrum. Okay? So given x of t, you can compute the frequency domain, and given the frequency domain, you can compute the time domain signal. So these two expressions form what we call a Fourier transform pair, okay? Because given one, you can always compute the other. So we refer to this capital X as the Fourier transform of the signal x of t, and refer to this x of t as the inverse Fourier transform of this spectrum capital X, okay? And these two forms what we call a Fourier transform pair, okay? So this is super important, okay? If you remember only one thing from this class, this is probably the formula you will remember, okay? So, any signal x of t, you can uniquely represent it in terms of its frequency domain signal. And then given any frequency domain signal, you can always convert it to the time domain signal, right? So this is a unique one-to-one relation. Okay. All right. Now, for continuous time signals, a natural thing to ask is when does this, expression hold, right? When does this expression hold? So the existence of this expression mostly follows from the conditions for the Fourier series representation in the periodic case, okay? So I don't want to go into details of this, but you can sort of see the similarities here. So the question is, when does this, right, when does this integral here, right, let's denote it as x hat, provide a valid representation for the original signal x of t, okay? So this representation, right, this Fourier transform exists. Right, if you're looking at a L2 convergence, L2 type convergence, then this requires x of t to have finite energy, okay? So previously, for periodic signals, we require x of t to have finite energy over one period, okay? But now we're assuming the period goes to infinity, right? So we're basically saying that the signal x of t itself has finite energy, okay? Or if you're looking at almost everywhere convergence, or convergence except at these discontinuity points, then you would want to satisfy the set of Dirichlet conditions. Right? So this includes x of t being absolutely integrable. Okay, so first for L2, you need finite energy. So for this almost everywhere convergence, you need absolutely integral finite maxima and minima over any finite interval and finite number of discontinuities, okay? So you can see that all of these conditions sort of are inherited from the, periodic case. All right, so that's, I think my time is up, but the remaining is just a few examples, okay? So tomorrow we'll just go through some of these examples, but the main points we already delivered.